Welcome to Study Loop.
We need to find the sag-to-span ratio, knowing that the tension at this point B is at a minimum value. And then we also need to find the value of this angle theta and also the value of that tension T. So I'm going to start the problem by first writing the equation for the length y of B. So y of B we know is going to be equal to c times the hyperbolic cosine of L over 2 divided by c. And then the tension T, which I'll label Tm, is going to be equal to the weight per unit length times the length y of B. So we can take this expression for y of B and plug it into this term for Tm. So we can rewrite this as W times C times the hyperbolic cosine of L over 2 divided by C. And what we're going to do next is we're going to take a derivative of Tm, take a derivative on both sides of this equation, and set it equal to 0 to solve for our minimum value for that tension. So we take a derivative of Tm with respect to C, and that's now going to become W times the hyperbolic cosine of L over 2 divided by C minus L over 2 divided by C times the hyperbolic sine of L over 2 divided by C, and we're going to set that equal to 0. So after setting it equal to 0, we can then rewrite it as the hyperbolic cosine of L over 2 divided by C, which is equal to L over 2 divided by C times the hyperbolic sine of L over 2 divided by C. And then further simplifying, and then we have this hyperbolic sine and hyperbolic cosine, which we can write as the hyperbolic tangent L over 2 divided by C is equal to C divided by L over 2. And what we can do here is we can take this term here, we can solve for this term here to get a numeric answer. So we rewrite that solving for that term, L over 2 divided by C, and we'll get a numeric answer that's equal to 1.1997. So what we can do with this is we can take this numeric answer here and plug it into the equation for y of B here. And we're going to divide by C on both sides to get a numeric answer on the right side. So I'm going to rewrite that equation and divide both sides by C, and we're left with the hyperbolic cosine of L over 2 divided by C. So we now take this term, this number here, and plug it into this term here. So we'll have yb over C is equal to the hyperbolic cosine of 1.1997 and that will give us an answer of 1.8102. So now the equation for the sag H divided by the span L, that's going to be equal to H over C, this ratio of the sag to the length L, divided by 2 times L over 2C. So since we know the ratio of the length YB to C, we can then write the ratio of H to C we can write that ratio H of C as just 0.8102. And then this term, L over 2C, we already calculated it to be 1.1997. So the sag to span ratio is going to be equal to 0.338. So we're now going to find the angle theta, the value of the angle theta, and the value of the tension T. So I'm going to label the tension T naught in our free body diagram. So we're going to have the tension T naught going in this direction, T naught. So we can write that T naught is equal to the weight per unit length times the length C. And we also know that the tension, this tension Tm, is equal to the weight per unit length times the length C times the hyperbolic cosine of L over 2 divided by C. So we're going to take T naught and divide it by Tm. So we're going to have Tm divided by T naught, which is going to be equal to Wc times the hyperbolic cosine of L over 2 divided by C, and then divided by Wc. And then these terms are going to cancel. So W and C cancel. So we can rewrite this as just the hyperbolic cosine of L over 2 divided by C. And if we go to a previous calculation that we did, we see that this y of b over c is equal to this hyperbolic cosine of L over 2 divided by c, which is also what we just calculated. So we can then say that this is going to be equal to y of b over c. So now we have that the tension T naught is going to be equal to Tm times the cosine of theta. And we got this by looking at the free body diagram and relating that the cosine of theta to these tensions, right? Since this is adjacent, this is the adjacent side, and this is the hypotenuse side. So then we can rewrite this as Tm over T naught as equal to the secant of theta. So this angle theta, so again, we're going to rewrite this solving for the angle theta. And that's going to be equal to the secant inverse of Tm divided by T naught. And we can replace this Tm over T naught with y of b over c. So again, we rewrite it as theta is equal to the secant inverse of y over b over c. And we've already calculated the value of y of b over c. So we can now say that the angle theta is equal to the secant inverse of 1.8102, and that will give us an angle theta that's equal to 56.5 degrees. And now to solve for our tension T. So again, I'm going to write that the tension T, Tm, is equal to the weight per unit length times the length y of b, which we can then rewrite as W times y of b over c times 2 times c over L times L over 2. And we can plug in the known values. So I'll rewrite Tm is equal to W times 1.8102 times 1 over 1.1997 times L over 2. And then we can rewrite this as 0.755 times the weight per unit length times the length L.